In the second part of this course, we will be looking at the simulation of biosystems. So the definition of a biosystem and how to model it should have been seen in the course Process Modeling and Control. Some examples of biosystems might be a water cycle, for example, where you look at or you want to model the water quality in function of the sewage infrastructure, the presence or absence of calamity basins in the system, whether or not there is water purification in place, and so on. Food-wise, we might be thinking about modeling the growth or the non-growth of certain crops based on stress factors and environmental conditions. For MBT, an option would be to look at how to transform, how to model an amino acid chain into a 3D protein. So for that, you would be needing the order of the amino acids, the reactive groups that are present, how are the charges divided, so positive and negative charges, and so on. So if you recall the definition of a system, you could say that a system is a combination of different parts which in their entirety form or they serve a certain purpose or a certain function. So it's a combination of parts that as a whole, so when we look at all parts together as a whole, they have a certain purpose or a certain function. A system is always located in an isolated part of the universe. So we will not be looking at the entire universe, but only a part of the universe. For example, if you think back at the water cycle, we don't care about the water quality all over the world. We are looking at the water quality for a certain city or a certain river. So a certain location which we are interested in, not the entire universe. And then a system is normally obtained by linking different processes. Next to the system, you also have the system environment, which basically are all the parts of the universe which interact with the system. So it's everything in the universe that has a certain interaction with the system and which just might influence the system as well. And then between system and system environment, there is a system boundary. So the biosystem, at first you model it, so you translate it into a set of mathematical equations which are very often differential, so differential equations. And then what's important to remember is that a model is always an approximation of the reality. So since you don't know all the variables which should be included in the model, or you cannot measure all the variables which should be included in the model, you can never get a model which is an exact replica of the true underlying biosystem. But what you do in modeling is you look for the best model that you can get, so you will try to approximate the biosystem as good as possible through a set of mathematical equations. The second thing that you can do then is simulate. So a simulation, what you do in simulation is you use the mathematical model in combination with certain tools to find an optimal system. So use mathematical model in combination with some tools to get an optimal system. So important is we are looking here for an optimal system, not an optimal model. So we are playing with the different parts that constitute the mathematical model, and we will see how to or what to change to improve to get to the best system, biological system possible. And then in combination with the tools that I'm talking about are the different chapters that we will be treating. So parameter estimation, uncertainty analysis, sensitivity analysis, and these things. So what you do is you experiment with the model. So basically what you do is you imitate the behavior of the model to see what happens if you change certain things. So experimenting with the model happens virtually, so it happens manually or computer-based, but we will not be changing the true model. So we will not be installing different sewage systems and see which one is best. We cannot do that. We cannot install a calamity base and see if it works, if not place it on another system or another location. So what we do is we do all those things virtually in a computer model to see what is the best setting, the best setup, the best strategy. And then if we found this best strategy virtually, we will implement it in reality. So there are a lot of calculations involved. Calculations can be done analytically, meaning that if we have the set of equations, so we have explicit equations and they are solvable, then we can just solve the equation and get a solution. But in reality, they are not, well, we don't necessarily know all the equations, and especially they are not necessarily solvable. So what happens is we rely on numerical methods. So we will use numerical methods to find a solution of the system. So if you want to represent the simulation of a system, you can look at it this way. So we have, on the one hand, the biological system, so the system under study. Based on this system, we will do analysis, we will do experiments, we will make observations, and we get to experimental data, so through analysis, observations, and so on. And the process to go from the system to the experimental data is not a straightforward process. So you do certain things, you sometimes have to take a step back before you can move on, and so on. So this is the thing that happens in the real world, so the real life, the reality. If we then go to the virtual world, we do a model. So we make a mathematical model. And with this mathematical model, we will perform simulations. We will perform simulations to get to a better model, to a best model prediction. And then we will be using the experimental data to confirm the hypothesis that we have for the best model prediction. And so through simulation, we will get to an optimized model. So the optimal model virtually, which corresponds to the optimized system in reality. So once we have an optimized model, you can then implement it in reality to get to an optimized biological system. And so going from the model to the optimized model, that's what's the important part. That's what the simulation is all about. So purpose of modeling, there are several purposes. It might be to understand and analyze the properties of the system. You might want to predict the behavior of the system under unknown circumstances. You might find or might want to find conditions to get to optimal performance. So optimal performance would be least cost production, maximal output, best river quality, optimal growth, those things. Or you want to look at how can I modify my system to obtain a desired behavior. So I have a certain behavior that I want to get out of the model. How do I change the model? So what do I have to put in place to get the system that I want? So the last thing is through process control. What we will be focusing on is how do we find the conditions for optimal performance. And so we will be using computer power. Why? Because it's just easier. So computer power allows us to do more calculations than manually, faster calculations than manually. We can use more complex models because we don't have to do things ourselves or with the human brain. We can rely on the computer. So in the end, we will leverage the fact that computers are stronger, faster, and more performant than the human brain, and we will use computer power to get to the optimized model.